At 6:35 in the morning, Universal Time on August 5th, 2026, a hollow steel tube the size of a school bus slammed into the surface of the moon at roughly 5,400 miles per hour, and there was absolutely nothing anyone on Earth could do to stop it. Nobody tried, because nobody could. No engine, no fuel, no way to steer it away from its target, no last-minute course correction available to anyone watching. For 18 months, gravity and sunlight had been quietly nudging this piece of forgotten rocket hardware toward a collision that astronomers watched coming with mounting certainty, refining the predicted time and location with each new observation. And when the impact finally happened, it was not a surprise. It was a scheduled event, tracked down to fractions of a second, that scientists around the world had specifically set their instruments to capture. Within minutes, telescopes in Chile detected the chemical fingerprint of the blast, isolating specific elements within the expanding cloud of debris. Within a day, a South Korean spacecraft orbiting the moon sent back images showing a dark new scar that had not existed 24 hours earlier. This is the story of how a piece of a SpaceX rocket, launched more than a year and a half earlier for a completely different mission, ended up carving a brand new crater into the lunar surface, why scientists treated the whole thing less like a disaster and more like the scientific opportunity of a lifetime, and what it reveals about how genuinely crowded the space around Earth and the moon is quietly becoming as launch schedules accelerate across nearly every spacefaring nation on the planet. To understand how this happened, you have to go back to January 15th, 2025, when SpaceX launched a Falcon 9 rocket from Kennedy Space Center in Cape Canaveral, Florida, carrying 2 separate lunar landers on a single flight, part of a growing trend of pairing multiple independent lunar payloads onto shared commercial launches to cut costs for everyone involved. One was Blue Ghost, built by the American company Firefly Aerospace as part of NASA's Commercial Lunar Payload Services program. The other was Hakuto R Resilience, built by the Japanese company ispace. 2 spacecraft, 2 countries, 1 shared rocket ride, the kind of mission SpaceX now runs almost routinely. Both landers separated from the rocket's upper stage and continued on toward the moon independently. Blue Ghost succeeded, touching down and operating on the lunar surface for roughly 2 weeks exactly as planned. Hakuto R did not, failing to complete a safe landing. But the part of the story that matters most happened after both landers had already gone their separate ways. Once the Falcon 9's upper stage finished its job boosting both spacecraft toward the moon, it had nothing left to give. No remaining fuel, no propulsion, no way to actively control where it went next. It became, in the language scientists use, space junk, a hollow metal cylinder roughly 39 feet long and 13 feet wide, weighing somewhere in the range of 8,800 to nearly 11,000 pounds, depending on the estimate, cataloged under the designation 2025 or 010D. Under normal circumstances, this kind of leftover rocket stage doesn't stick around for long. Most Falcon 9 upper stages remain in orbits relatively close to Earth, where atmospheric drag eventually pulls them back down and they burn up harmlessly on re-entry, a clean, unremarkable end. But this particular stage ended up on a much wider, looping trajectory through the Earth-Moon system, spending extended periods of time out near the moon itself rather than staying close to Earth. Out there, far from Earth's atmosphere, different forces begin acting on an object drifting with no propulsion of its own. The combined gravitational pull of the sun, the Earth, and the moon all tug on it simultaneously. And there's something else most people never think about. Sunlight itself exerts a small physical push on objects it strikes, a phenomenon called solar radiation pressure. It's an incredibly gentle force, barely perceptible in any single moment, but over roughly 18 months. That combination of gravitational tugging and the steady, quiet pressure of sunlight slowly bent this rocket stage's path into something new. Tracking data later showed the object had actually been observed more than 1,000 separate times over that period, each observation refining the picture of where it was headed a little further. And the primary remaining source of uncertainty in the final prediction came specifically from how unpredictably that solar radiation pressure pushed on the tumbling stage as it slowly rotated through space. And that new path had a destination. An astronomer named Bill Gray is the person who figured this out. Gray isn't a household name and he doesn't make headline news every week, but he has spent roughly 3 decades tracking objects in deep space that most conventional monitoring systems simply overlook. Objects orbiting far beyond the range. Most tracking networks bother watching closely. He developed specialized software, used through his Project Pluto tracking initiative, specifically designed to distinguish between genuine asteroids and man-made debris that happen to be moving through similar orbital paths, and observatories conducting routine asteroid surveys regularly contact him directly whenever they spot something they can't immediately identify. In the months following the January 2025 launch, Gray began noticing that this particular Falcon 9 upper stage tracked and observed more than 1,000 separate times as its orbit slowly evolved, was heading somewhere concerning. He ran the trajectory calculations again and again over the following months as new observational data came in, and the picture kept sharpening. This piece of rocket hardware was going to hit the moon, not might. There was no fuel left to change course, no way to intervene from Earth in any way whatsoever. The outcome was locked in well in advance. Gray himself wasn't particularly alarmed by any of this. He later noted publicly that he had been anticipating exactly this kind of event for roughly 20 years, ever since large pieces of debris first started accumulating in orbits capable of theoretically reaching the moon. If anything, he said he was mildly surprised it hadn't happened more often already. Before this event, only one other object had ever been confirmed to strike the moon by pure accident, a piece of rocket debris that hit back in March of 2022. That earlier impact, initially misidentified before being traced back to a Long March rocket stage associated with China's 2014 Chang'e 5 T1 lunar mission, struck the moon on March 4, 2022. When NASA's Lunar Reconnaissance Orbiter later photographed that impact site, the images revealed something nobody expected. Not one crater, but two overlapping craters sitting directly beside each other, each roughly 100 feet across, a genuine double crater. Researchers concluded the hollow rocket body likely had uneven mass distributed along its length, causing its kinetic energy to release in two nearly simultaneous separate impact points rather than one. Exactly the kind of strange, previously unseen data point that only comes from studying an actual real-world impact rather than a theoretical model. Gray has said publicly that this second confirmed impact, arriving roughly 4 years after the first, generated considerably more advance attention than he originally expected, including sustained interest from people well outside the astronomy community, who had never previously followed his tracking work at all, a shift he attributed partly to how much more advance notice this event offered compared to the largely retrospective coverage the 2022 impact received once its double crater was finally photographed months later. As the months passed, following Gray's initial 2025 tracking, the predicted impact time for this second event grew steadily more precise. By his final tracking update in the days immediately before impact, the estimate had narrowed to roughly 6:35 and 37 seconds universal time on August 5, 2026, translating to about 2:35 in the morning Eastern Daylight Time in the United States. The predicted impact location sat near a crater called Einstein, close to the moon's western limb as seen from Earth. This time, scientists at NASA, at independent observatories, and at research institutions around the world had months of advance warning to prepare. Ordinarily, when natural objects strike the moon, whether from asteroids or meteoroids, they arrive completely without warning, leaving scientists no opportunity to point instruments in advance. This event was different. A known object, of known mass and known dimensions, was going to strike a known location at a precisely known time. That combination almost never happens in astronomy, and researchers treated it as a genuine gift. On July 17, 2026, a team of 23 researchers published a detailed scientific paper specifically laying out observational planning for the upcoming impact, calculating optimal viewing angles, ideal timing windows, and identifying which telescopes and instruments stood the best chance of capturing either the initial impact flash or the resulting ejecta plume of lunar dust and debris. The paper noted the impact would occur on sunlit terrain near the moon's western limb, with an expected impact velocity of roughly 2.43 kilometers per second, striking at an angle of about 34 degrees from vertical, and pointed out that a South Korean lunar orbiter would happen to pass in close proximity to the impact site right around the moment of collision. Researchers involved in similar modeling work predicted the resulting dust plume would rise somewhere between roughly 45 and 60 meters above the lunar surface before spreading outward, with the expanding cloud potentially visible through sensitive telescopes equipped with high-speed video capture for the first several minutes following impact, appearing many times brighter than the surrounding dark lunar sky during that brief window. Because the rocket stage was expected to strike at a relatively modest 2.43 kilometers per second, considerably slower than the far higher speeds typical of natural meteoroid impacts on the moon, researchers cautioned in advance that the initial flash itself might prove difficult to observe clearly, since a larger share of the impact's total energy was expected to go into excavating and ejecting material rather than producing a bright, easily visible burst of light. Then, on August 5, 2026, at 6:35 in the morning Universal Time, the rocket stage actually hit. The European Southern Observatory's very large telescope, positioned in Chile's Atacama Desert, had been aimed directly at the predicted impact zone and stood ready, alongside numerous smaller observatories and amateur astronomers across the Americas who had spent weeks preparing their own equipment based on the published campaign paper's recommended viewing windows. Astronomers across the Americas had their own instruments similarly positioned. The roughly 4,900 kilogram hollow metal tube, struck the lunar surface at approximately 8,700 kilometers per hour, close to 5.5 kilometers every single second. With no atmosphere on the moon to slow anything down before impact, the full kinetic energy hit the surface essentially unimpeded, releasing an estimated 14.5 billion joules of energy, roughly equivalent to 3 tons of TNT detonating on the spot, or somewhere in the neighborhood of 15,000 sticks of dynamite going off simultaneously in one location. Within minutes, instruments captured chemical signatures and the resulting plume of ejected material, detecting both sodium and lithium. Researchers believe the sodium originated from the lunar soil itself, since the moon's regolith naturally contains sodium compounds that get released when struck violently enough. The lithium almost certainly came from a different source entirely, the rocket stage's own onboard batteries, vaporized and scattered as gas by the force of the collision. A genuinely remarkable moment where chemical evidence from both the moon and the man-made object that struck it appeared together in the same expanding cloud, drifting through space for roughly 5 to 10 minutes after impact before dispersing, giving spectroscopy teams a rare direct opportunity to distinguish native lunar material from artificial hardware within a single observed plume. The following day, on August 6th, South Korea's National Space Agency released a set of images captured by its lunar orbiter, Danuri, which had been specifically repositioned in advance to observe the predicted impact zone. Mission planners had the spacecraft conduct a series of 8 separate imaging passes in total, one captured roughly 30 minutes before the predicted impact time, followed by 7 more taken afterward at planned intervals. Lining those before and after images up side by side reveals a distinct dark streak present in the later images that simply wasn't visible beforehand, a fresh mark newly etched onto the lunar surface. The exact dimensions of the resulting crater are still being refined, but early estimates place it somewhere between roughly 20 and 30 meters wide, or about 65 to 100 feet across, noticeably smaller than what a solid object of comparable mass, such as a metal asteroid, would typically carve out. That size difference comes down directly to the rocket stage being hollow rather than solid. When a hollow object strikes at high velocity, its kinetic energy distributes differently through the material and into the surface than it would for a dense, solid impactor. And researchers are studying exactly how that crater's shape and size differs from typical natural impacts, as a way of better understanding how human-made hollow objects behave differently from natural ones, building directly on lessons already drawn from the unexpected double crater shape observed after the 2022 impact. NASA's Lunar Reconnaissance Orbiter, which had already imaged the target region beforehand, specifically to establish a clean baseline for comparison, is expected to pass over the fresh impact site in the coming weeks. And its onboard camera is capable of resolving surface features as small as roughly 50 centimeters across, promising a considerably sharper, higher resolution look at the new crater than anything captured so far. What makes this particular event scientifically valuable extends well beyond simple curiosity. NASA, SpaceX, and a growing roster of other space agencies and private companies are all actively working towards sending humans back to the lunar surface within just the next few years. NASA's Artemis program has already assigned its crew for the Artemis 3rd mission, currently targeted for 2027, intended to land astronauts near the moon's south pole for the first time in human history. SpaceX plays a central role in that plan, with its Starship vehicle, the largest rocket ever built, designated as the system responsible for actually landing those astronauts on the surface. In October 2025, SpaceX successfully completed the 11th test flight of Starship, splashing the vehicle down safely in the Indian Ocean, a milestone widely described at the time as a significant step forward toward eventually carrying human crews to the moon. But before any of that can happen safely, scientists genuinely need to understand exactly how the lunar environment responds to impacts in far greater detail than computer models alone can provide. They need real data on how lunar dust behaves when something strikes the surface at speed. They need to understand precisely how craters form under different conditions, including how a hollow, unevenly distributed mass, like a spent rocket stage, behaves differently on impact than a solid, uniformly dense natural object, such as an asteroid fragment. They need to know how ejected material distributes itself across the surrounding terrain after an impact, and how far that ejected debris can realistically travel before settling back down in the moon's much weaker gravity. Because once astronauts are regularly walking on the lunar surface, once permanent structures start getting built there, and once spacecraft are launching and landing on a recurring basis, impacts and debris genuinely become active safety concerns rather than abstract academic ones. An astronaut working on the surface cannot risk being struck by fast-moving ejected rock fragments. Habitats and equipment cannot afford to be damaged by debris kicked up during a nearby impact, whether that impact comes from a future spacecraft landing too close to existing infrastructure or from an entirely separate piece of incoming debris. Real observational data, rather than purely theoretical modeling, is directly useful for building the kind of safety margins future lunar missions will actually depend on. And researchers involved in planning the August 2026 observation campaign have specifically noted that calibrating existing computational impact models against genuine before and after imagery is exactly the kind of ground truth data those models have been missing. There's also a more complicated dimension to this story worth being honest about. Juliana Schiemann, SpaceX's director of NASA Science Mission Management, addressed the situation publicly in the days leading up to the impact, explaining that the stage had been properly passivated according to existing disposal guidelines, meaning its remaining fuel and batteries had been safely depleted or disconnected before it was abandoned, and that the trajectory ultimately leading to the lunar collision was unintentional but effectively unavoidable, given the vehicle's remaining fuel reserves once its primary mission was complete. That's a reasonably candid admission. Nobody at SpaceX is claiming this outcome was planned, or that it represents ideal practice. The company has said it is now working directly with NASA on measures aimed at preventing similar unplanned trajectories from developing on future lunar missions, including potentially reserving a small margin of extra propellant specifically for post-mission disposal maneuvers, rather than leaving spent stages entirely at the mercy of gravity and sunlight. Bill Gray, the astronomer who originally tracked the object, offered his own blunt assessment that circulated widely once the story broke, quoted repeatedly across science outlets and mainstream news coverage alike in the days surrounding the impact. He noted the event posed no immediate danger to anyone, but said it did highlight a certain carelessness in how leftover space hardware gets disposed of once its primary job is finished, adding simply that things are getting crowded up there. That particular phrase is likely one people will hear repeated more often in the years ahead, echoed already by other astronomers and space policy commentators discussing the broader implications of the event. Hundreds of thousands of individual pieces of debris currently orbit Earth at various altitudes. Most are small and reasonably well tracked, especially in low Earth orbit, where clear disposal guidelines already require spacecraft to re-enter the atmosphere within a defined window after completing their missions, specifically to limit how long they linger as debris. But objects that end up on higher, wider orbits, the kind this particular Falcon 9 stage drifted into, fall under rules that are considerably less strict and less consistently enforced, and Gray himself has acknowledged that he is essentially the primary person actively tracking this specific category of high-altitude junk, work he largely does alone, without much public recognition, one calculation update at a time. Space, in the meantime, is only getting busier. SpaceX alone launches dozens of Falcon 9 missions every year. Other companies and national space agencies around the world continue ramping up their own launch schedules, with China in particular dramatically increasing its overall launch cadence in recent years. Private companies across multiple countries are sending commercial landers toward the moon with rising frequency as the broader lunar economy expands. Every one of those launches leaves behind some combination of spent upper stages, payload fairings, and other hardware that has to end up somewhere once its job is finished. The overwhelming majority of that material burns up safely on re-entry or ends up in orbits with negligible long-term risk, but clearly not every piece follows that pattern. The fact that only 2 confirmed accidental rocket impacts on the moon have occurred across roughly 6.5 decades of human spaceflight is, statistically speaking, a fairly remarkable track record given the sheer volume of hardware launched into space over that span. But as launch activity continues accelerating year over year, that historically low number is unlikely to stay quite so low indefinitely. And the lunar surface itself is about to become a far more active, far more crowded place than it has ever been in human history, with NASA and China both actively planning crewed missions, robotic rovers from multiple nations already operating or scheduled to operate on the surface, and commercial landers touching down with increasing regularity. If rocket debris begins striking the moon more frequently going forward, and if any future impact happens to occur near active missions, equipment, or eventually human crews, the consequences could carry considerably more weight than this particular event ever did. Some researchers tracking this issue have already begun calling for clearer, more consistently enforced international guidelines, specifically covering how spent hardware on high-energy, moon-crossing trajectories should be disposed of, arguing that the existing rules governing low Earth orbit simply were not designed with this particular category of wide, looping orbit in mind, and that the gap in oversight will only become more consequential as lunar traffic increases. So this impact, dramatic and strange as it genuinely was, ultimately functions as something closer to a useful early warning than a disaster. A school bus-sized rocket stage struck the moon, carved a brand new crater into its surface, and released a plume of sodium and lithium gas that lingered in space for nearly 10 minutes before dispersing. It was photographed by a South Korean spacecraft, chemically analyzed by one of the most powerful telescopes in the entire southern hemisphere, and predicted, tracked, and meticulously documented months in advance by a small, largely unheralded network of astronomers who do this exact kind of painstaking work quietly, year after year, well outside the spotlight of mainstream headlines. There's something almost poetic about how the whole sequence unfolded. A rocket originally built to deliver two separate lunar landers, representing two different private companies from two entirely different countries, ultimately ended up making its own unplanned trip to the moon in the most uncontrolled way imaginable. It didn't complete a soft landing. It didn't accomplish any mission objective. It simply crashed, leaving behind a permanent mark near Einstein crater that will remain there essentially forever, since the moon has no atmosphere, no wind, and no erosion to gradually smooth it away. Long after SpaceX, long after every person currently alive today, that crater will still be sitting there on the lunar surface, an enduring physical record of an event nobody ever actually intended to happen, a permanent footnote on a world that otherwise preserves almost nothing of its history, the way Earth's own weather and geology constantly erase and rewrite ours. Scientists are now working through the before and after imagery captured by Danuri, analyzing the spectroscopic readings gathered by the Very Large Telescope, and waiting for the Lunar Reconnaissance Orbiter to pass directly over the site and deliver a sharper, more detailed look at the resulting crater using its narrow-angle camera, capable of resolving surface features down to roughly 50 centimeters across. They're writing follow-up papers, refining their computational models, and updating simulations that will eventually help keep future astronauts genuinely safer once crews actually step onto the lunar surface as part of the Artemis program. Work that mission planners have said will directly feed into how landing zones and safety buffers get calculated for future crewed and robotic missions alike. That's often how real science tends to work in practice. It isn't always clean, tidy, or fully planned in advance. Sometimes the most genuinely useful data comes directly from something nobody intended to happen at all, a forgotten piece of hardware drifting quietly through deep space for 18 months, nudged along by gravity and sunlight, forces gentle enough to barely register moment to moment until one specific morning at 6:35 Universal Time, it finally arrived precisely where those accumulated forces had been steering it all along, not carrying a mission, not carrying a crew, just carrying momentum. And one astronomer, who had quietly been watching for events exactly like this one for roughly 30 years, mostly alone and mostly without public recognition, saw it coming months in advance. There was no single dramatic realization. As Gray himself has described it, the certainty simply built up gradually, one tracking update at a time, until the outcome became unmistakable. The moon gained a new crater on August 5th, 2026. It was not the first time this has happened, and it almost certainly won't be the last. But it was, by a wide margin, the most closely observed, the most thoroughly anticipated, and in several genuinely meaningful ways, the most scientifically useful lunar impact humanity has ever witnessed. Because what researchers ultimately learned from this single, unplanned collision stands to directly shape how humanity returns to the moon in the years ahead, and how future missions try to leave considerably less of their own hardware scattered behind. When they do, one tracked object, one calculated trajectory, and one carefully aimed telescope at a time.